So good evening to everyone here in Corning, and a special welcome to those of you who are joining us online for the special Connected by Glass event. My name is Catherine Larson, and I am the Manager of Curatorial Affairs and Curator of Ancient Glass here at the Corning Museum of Glass. And it's my pleasure to welcome you all tonight to the celebration of the world premiere installation of Glass Bridge, an architectural and engineering marvel that truly pushes the boundaries of what is possible in glass, a material that we, of course, here love so much. For our program tonight, we will hear from the 4 collaborators who designed, engineered, and executed the bridge, led by Dr. Masoud Akbarzadeh, Associate Professor of Architecture and Director of the Polyhedral Structures Laboratory at the University of Pennsylvania, who is the lead designer of the project. We'll close with a panel discussion and Q&A from the audience, in person and online. And at the close of the panel, for those of you who are joining us here in Corning, we'll have the opportunity to go upstairs and look at the bridge in the galleries and really see the wonder that it is. But before we hear from Dr. Akbarzadeh, we have a special teaser for a forthcoming documentary produced by, about the Glass Bridge, produced by Greenhouse Media. So with that, please enjoy.
When we link principles and theory to art and practice, that's when science becomes meaningful.
What is so special about this project here, it's somehow in between arts, science, and engineering.
So the question is, if glass is a material that is going to be constantly used in the field of design and architecture, do we know really how to come up with better structures that are made out of glass? And do we know how to take advantage of the structural capacity of the material itself? We really want for the glass to do everything, from the load bearing to the aesthetics to the construction techniques.
Glass Bridge is a manifestation of a narrative that architecture could create elegant, efficient structures, although that they might look daunting and impossible in the first glance. These sorts of structures follow the rules of nature. When you look at the skeleton of animals, when you look at the tree, everywhere you could see all these tension compression systems that efficiently distribute the material where exactly is needed.
We're doing actually what has been used by engineers and architects since medieval times and probably earlier than that. What's unique about what we're doing, I think, is the material that we're using, but also number 2, the modular approach that really lends a degree of flexibility in your ability to construct.
We're used to thinking about glass as being a really fragile material. And one of the things that this project does is disrupt that narrative.
Glass, it's the only transparent material with such a durability that we use it everywhere, from facades to cars, from the screen we are talking.
We wanted to really push the construction methods related to glass. We wanted to show how you can be innovative with the use of material, how you can minimize the use of material without compromising the function. And then we also had intentions to create an elegant structure. We wanted to exercise all these techniques in order to show you can take advantage of the existing technology into making these pieces that are quite efficient.
The brilliance and the success of this bridge is not only in its innovation, but it's in its beauty.
This is just an example, a gate that opens all the opportunities for future architects and engineers that look at the conventional way of building structures and say, okay, as a second thought, we might approach this differently.
My only hope is to open a door for future explorations, to look into innovative methods of constructions that are more efficient, environmentally friendly, and reduce carbon footprint. We are trying to depict a better future for ourselves and also for the next generation to come.
Hello again. Welcome, everyone. My name is Masoud Akbarzadeh. Thank you very much, Kate, for the introduction. I'm really glad to be here. And I really appreciate all of you guys taking time to attend this session tonight so we can give you a little bit of glimpse into the production, design, engineering, and the background about this class. So first of all, I have to say I have been super lucky and to have excellent collaborators, individuals who helped us through the entire process, from the design to the construction, including Professor Dr. Joseph Yost from Villanova University, Dr. Bolhassani, City College, New York, and Professor Jens Schneider. And I had the privilege to work with super talented individual students. My former PhD student, Dr. Yao Lu, who is not here, unfortunately, couldn't, but now he's a professor at Jefferson University, Dr. Pariya Artano, who is working on the analytical aspects, and everyone. There were many, many people who worked on this project. I would also thank Ms. Laurie Cantor-Trish for making this piece possible by supporting us from the earliest stages of the design and construction. And obviously, the Dean Schneider at the Weizmann School of Design. A lot of people to thank, but it's necessary because I'm going to open up my presentation by giving you a hint about the design philosophy behind this work. Because every time we, or I actually share this result with everyone outside of the loop, they would ask, okay, that's great, but why glass? Are we gonna scale this up? Are we gonna build this in real world, exposed to the world outside? Why glass? So we know why glass because we're at Corning. You're very much familiar with the work that has been presented at Corning. But I'll walk you through the reasoning behind the work and how this would actually contribute to the field of construction. So if you don't know, you might know with this slide that construction industry is responsible for almost 50% of annual carbon emission. And this includes embodied carbon and operational carbon. Embodied carbon is the amount of material and the process and energy and carbon that goes into the production of construction material together with the techniques that we build buildings. This would stay with every building that we built throughout its life. So you cannot change it. Operational energy, that's another thing. You can just invent new methods of HVAC system. You can improve that system, you can change it. But one thing that stays with the building, that's the material and the method of construction. So how we can reduce that footprint by looking into that method. And myself and my team, for the past 20 years, we've been trying to come up with novel ways to help us reduce construction material. The inspiration obviously comes from nature. Many of you have seen this image before. Nature is a master in finding a way to redistribute the material where it has to be, to create lightweight structures that are functioning really well, and through millions of years of evolution. And that inspired many engineers and designers for the past 300, 400 years in the field of construction to come up with these structural systems and forms and geometries that help them redistribute the force internally so they can be efficient. So for your information, Robert Hooke, 500 years ago, suggested a really, really interesting method of construction and design, and that was a hanging chain. Why this is super interesting? He said that if you hang a chain from two ends, it would form a spatial geometry. And what is so special about that geometry is that that is a geometry that is in pure tension. So everywhere you cut a section through that chain, it's in pure tension. So there's no bending moment, no twist, anything. So material actually follows the direction of the force. More interestingly, if you reverse that form, it would give you a pure compression. That is really, really interesting because at the time, let's say for the past 100 years, people used to work with masonry material only, and that's the only force that masonry can take. So they had to follow these rules. So this became a design methodology historically. 200 years after, mathematicians looked at these forms that we refer to as funicular or catenary forms. Funicular means that the form is actually carrying the forces in the form of pure tension, pure compression. And they realized that you can geometrically describe these properties by creating a closed polygon around every node. And if you measure the length of each edge of that polygon, it would tell you how much force goes into that node to keep the structure in equilibrium. This is super interesting because to come up with the form that is efficient and funicular is difficult. But we know that you can actually design a force diagram that represents the equilibrium of that form. And from that force, you can extract the form that is in either pure compression or pure tension. And everything is just pure geometry. You don't have to do any calculation. It's just pen and pencil. So this method was used extensively in the past. If you're familiar with Antoni Gaudi, he used both hanging chain models for creating Sagrada Familia and graphic statics, which is the basis of this geometry-based method that I described. Furthermore, the examples of great Swiss bridge engineers, Robert Maillart. He used graphic statics with geometry-based structural design method to build his structures. And for your information, Eiffel Tower has been designed using the same methodology. In 2016, I was lucky to be among the people to extend this method after 150 years from 2-dimension to 3-dimension, where the equilibrium of forces could be represented by a closed polyhedron instead of a closed polygon. In this case, you measure the areas of the faces of those polyhedrons, and that tells you how much force goes into that. And more importantly, you can start by designing your force diagram as an aggregation of these solids together that describes the force equilibrium and extract a variety of different spatial structural forms that are efficient, either in tension or compression. So we've tested this with many, many examples in my lab. For instance, this sample is only 24 pounds, and it can take the load of 4 elephants, 55,000 pounds. Or we design structures that are pure compression in the body, and the relative density is actually very close to the relative density of a human bone, that mass that is distributed in the space. So we have applied this to a variety of different structures. For instance, in this case, this structure can take 10 times more load than a conventional post and beam with the same amount of material, right? And you can apply this to the design of floor system, and you can reduce the material, for instance, from 30% to 50%. All good, great, but why glass? All right, so quickly, why glass? So we claim that we have a methodology that can design efficient structures. We can reduce the amount of material, we can reduce footprints. Why glass? So we all know that glass is actually one of the most important materials to work with. From the phone in your pocket to the envelope of buildings. And many, many people, let's say designers and architects, they would start to use the glass more because of its elegance, right? So the question was, if we claim that we can design structures, can we design structures that are efficient out of the most brittle and challenging material to work with, which is glass? So for that reason, we picked that battle to say, okay, let's just design a super efficient, lightweight structure out of glass. There's another point for that. The forms that I showed you, they have an inherent limitation. These polyhedral geometries, they all consist of planar faces. So on one hand, they're efficient, on the other hand, they're limiting. But this is not a limit in the field of architecture because we work with material. We have to materialize the forms that we create. So if they consist of planar faces, that means that they're best in translating sheet-based material into constructing efficient systems. So glass makes sense in this sense because if we can build this out of glass, you can do this out of any other material, any other sheet-based material, like steel, you can do it out of aluminum, metal, concrete, etc., etc. There is another design aspect into it. Because we are using graphical methods, and we have full control over the geometry, we can redistribute the force in multiple load paths to get multi-layer compression dominant structure. This is very similar to the structure to, for instance, the backbone of a turtle, right? Now, I'm going to tell you another thing that relates the structural form to the construction module of the bridge. So this is the bridge itself. You see that the module, it's a polyhedral form. It consists of 24 cells, polyhedral cells, that we take advantage for construction later. And if you look closely at that structural form that we designed using the methods of polyhedral graphic statics, you can see that the equilibrium of each node is represented by a closed polyhedron But these put together to create a diagram that we call the force distribution diagram, from which this actual geometry of the bridge extracted. Now, if you move further, we wanted to, again, take advantage of this geometry. So we started to design the cells. So each unit is, in fact, one geometric, or let's say polyhedron, that consists of glass panels on the top and bottom, and the side face is made out of acrylic. The reason for acrylic is that because it's cheaper at the moment. We didn't have that much time budget to go with glass, but in the future, obviously, we can do that. So this is a scene where the glass units were produced in Germany, and we were lucky because Moritz from Glassbow Fritz is here tonight, so he can talk a little bit more into details. But we gave instructions to them to how to put it together because we did multiple studies in that, and then they translated into precise construction. So once you make this light-weighted structure, the most important thing is that how you deal with asymmetric loading scenarios, because your structure is light and that might actually cause some dislocations or displacement in the units. So we came up with an interesting detail, which is a mechanical detail, and that allows us to lock the units with each other. It's a dovetailing connection we refer to as butterfly connection. And that is the connection that held everything in place after we position the units. So everything is mechanical. You can actually take that and disassemble it. If needed, you can replace the parts, and the goal is to disassemble it and assemble it in another place. So the construction process was started similar to many other structural systems. We start with the formwork, which is wooden, and then we place the units one after each other. There is a particular sequence of assembly to that, because these butterfly connections could be inserted only in a certain location, so you cannot lock yourself in. So there was a process. So we could not interlock all the units together because of the difficulty of assembly. And the places that we could not insert butterfly connection, we were using a square section rod for better engagement of the units. So the design of the bridge was such that it had rotational symmetry. This 124 units are in fact 62 identical units that we basically start the construction from both ends, and they will meet at the mid-span of the bridge. And then we have this keystone to place and connect the two ends together. It was not an easy task to assemble because we had to make sure that everything is precise, and the construction tolerance is only plus minus 0.1 millimeter. Right? So we had to be very precise, and that was a little bit challenging. And this is the end piece. So what I showed and discussed was an overview of the reasoning and the design philosophy behind it. But it took us around 5 years to get to this point that we could build this and exhibit it and talk about it. What I'm going to talk next, and invite basically my collaborators to the scene next, is to give you a little bit of background. How did we get there? Because I did not talk about all the experimental studies that we did in order to understand the material behavior, unit behavior, and structure behavior, or the material studies, and numerical analysis needed to get to this point. So with this, I'll invite Dr. Joseph Yost to join me on the scene, and then he can expand on experimental work that he conducted. So that allows us to rely on glass as a structural material. Thank you.
Make sure I have the technology down. That looks good. Welcome, everybody. As Masoud introduced me, my name is Joseph Yost, and I am from Villanova University. And I have been collaborating with Masoud and Jens Schneider and Damon Bolhassani here since, I think it started in the spring of 2018. And it's really a phenomenal experience to be here and see the end result of all that has gone into our collaboration together. So my contribution to this evening is to show some of the background work that has taken place in the laboratory to justify the use of the material, which is glass, in the compression dominant form that we're using through the polyhedral graphic statics, And super important here is using the modular construction, okay? And that's a very unique aspect of this project. So I'm just gonna look at a couple of pictures here, and those pictures are correlated strongly to the bridge that we have here at the Corning Museum and its ability to function efficiently as a structural system. All right, so I'm going to start off with the fundamental unit here, and that is the HGU, the hollow glass unit. So once we conceived of this as our building block, then the first question we had to answer was, how strong is the building block? Okay, the system is only going to be as strong as its individual parts. So we built our first HGU in the structures lab at Villanova University, and this is from the fall of 2018. It's really amazing to look at this picture. But we had the float glass cut by a local fabricator. We assembled this in our structures lab using 3D printed guidance, a two-sided VHB tape, and we put the thing together in the lab, and we were really on the learning curve here. But the end result of what we created, just aesthetically, we were super excited about this thing and thought, I think we're really onto something here. If we can really develop this as a modular structural system, I think we're going to have a very, very unique form of construction. All right, so we built the hollow glass unit. We needed to answer the question, how strong is an individual hollow glass unit? And again, vocabulary is important here. We're talking about compression dominant structures. So we built 4 of these things eventually, and we brought them to the structures lab at Villanova University, and we loaded them in compression, which sounds easy, but to get something loaded in pure compression is actually a very, very challenging experience because you don't want to have any eccentricities in your loads. But nonetheless, here's a picture of our hollow glass unit in our testing apparatus. It was loaded with displacement and strain sensors so we could pick up the behavior of the structure as we loaded it to failure. So here is another detail of our test setup. Here is our hollow glass unit under test, and in the bottom right-hand corner there is a digital display that shows how much force in thousands of pounds is being applied to the structure. And if I cross my fingers and hit the good button, we should see a video here. And you can see that go up. It's going to stall at about 37,000. And then it's going to explode. So this super exceeded our expectations. Jens and Damon and Masoud and I looked, we'll probably get to 5,000 or 6,000 pounds. And we got up to 37,000 pounds. And we had one actually that got up to 42,000 pounds. So we were also very confident that not only is the system going to work, but it's going to have more than enough capacity to serve our demands. And this is just a simple picture. We could get into how it failed. It was flexural buckling, exactly what we wanted. All right, so the second test, we're doing modular construction, remember. So that means this piece is acting with this piece to form a system. Well, when you have glass and you have 2 pieces of glasses in contact with each other, that's a recipe for disaster. You have a brittle material in contact with a brittle material, you're never going to develop the capacity of the material, which we just saw is 37,000 pounds, just to put a line in the sand. You're never going to get there if you can't transfer the force within the system or between glass and glass. So we've needed a transparent interface material that could smooth out the stress concentrations that are going to occur where the glass is bearing against glass. This is a little more mundane. There's no exciting videos to look at, but it was a super, super important behind the scenes experimental system that gave us the results that we needed. We tested many different materials. A number of them did not get us the force transmission that we needed, but ultimately we came up with a material that did. This is the test setup. We spent over a year testing probably about 4 or 5 dozens of these things under different loading scenarios associated with cyclic and creep loading. And the bottom line is a fancy graph here. There's a horizontal orange line, that's the line in the sand that we wanted to get. And all of our colored bars or charts there exceed that. So we knew we had a material that would allow us to develop the capacity of our hollow glass unit. All right. Before we got to the 10-meter version of our glass bridge, we needed to experiment with a prototype system. All right, so Yao Lu, who was Masoud's PhD student at the time, built these hollow glass units at a company called Eventscape in New York City and built a 13-cell prototype glass bridge. And we named it, or Masoud named it Tortuga, which I think is very appropriate, tortoise in Latin. And we took Tortuga, we reconstructed it in the Villanova Structures Lab, and we tested it. And it's beautiful to look at these pictures because I spent a lot of time on the ground underneath that bridge, installing displacement sensors and soldering wires and just getting everything right so that when we did test this thing, we're getting meaningful data that objectively tells us how the system functions. So just a couple of pictures here. I drilled those bolt holes right there. I drilled and put those low displacement units together. I like to get my hands dirty. And then we tested Tortuga, and we got wonderful results. We tested it to what we refer to as the serviceability limit state in engineering terms, which means, okay, we design our structures to resist certain loads, service loads, and we design them to exceed that, but there's a service limit state, and this is what we expect the structure to see. And in terms of displacement, in terms of internal stresses and strains, we had very, very favorable results. And this is just some fancy graphs showing force and displacement and some strain measurement. There's nothing more beautiful than good data, and that's why I put this slide in there. But so that's a little walk down the path of experimental work that has led us to the 10-meter bridge that is here now at Corning. But there was a lot of stuff that happened in the lab, and it was a learning experience throughout all of these these experimental programs. But each time it was an enormous sense of satisfaction that, you know what, I think what we're proposing to do here, the way we're proposing to do it, i.e. the modular construction, and the use of the material being glass, were consistently reinforced by the experimental work that we have done in the lab. And just to throw this out there, we have a number of publications in peer-reviewed journals and conference proceedings, and Masoud may even have a slide at the end here. So if anybody's interested in learning about all this, our work is readily available through extensive technical publications. So it's been a pleasure to be here, and thank you. I'm sorry. I want to introduce my friend and colleague, Dr. Damon Bolhassani, and he's going to talk a little bit about the calculation and numerical part of the work related to our bridge. It's all you, Damon. Great seeing
you. When art and physics come together, architecture is born. In a way, art is the soul, and laws of physics are the backbone and skeleton of architecture. So in the next couple of slides, I will be talking about how we use these laws of physics in form of structural engineering and mechanics to rationalize the concept of glass bridge. From the very beginning, we had a lot of questions that needed to be answered. Questions like, we have the concept, but what thickness of a glass it would be appropriate for this project? What is the depth of this glass bridge that is going to work? It's going to be functional. What sorts of mechanics and connection we're going to introduce, and how the mechanics is going to work from one GU to the next one? What is the support situation? What sorts of thickness we need? So these are very important questions that we had no clue at the beginning of the project, but we need an answer in order to build this. And after answering those questions, there were more questions. Okay, if we know this glass with this thickness, with this depth of the glass bridge, how the final product is going to behave. What would be the deflection? What would be the behavior of this glass under its own self-weight? Or what if someone's going to cross it? Like we have a load, then how the bridge is going to behave, right? So these are valid questions, important questions that we have to answer in order to have a safe structure at the end of the day. Okay? So in order to answer those questions, we needed a working model, because at the time we didn't know even if we were going to do any tests. So we needed a working model that could predict accurately all these questions. And in order to do so, we, as a designer and engineers, we had two options. The first option was modeling the bridge on something that we call micro modeling, micro detail modeling, that is, consider every single detail that you see in the glass bridge, and what Masoud and Joseph were talking about, all those surfaces, connection. We need to model that accurately and then see how the structure is going to behave. The second option we had, which we call it macro modeling. So this is something that's kind of more rough in terms of modeling with a lot of simplification, and we could use that. Each model had its own advantages and disadvantages. I'm just going to show you some of those technicality difficulties and problems that we encountered during the modeling of the bridge. For instance, the interaction between side plates, locking bars, interfaces. So if you want to do a micro modeling, very detailed, you have to consider every single thing that you have in the bridge. And there are hundreds of pieces, thousands of interactions, and these are just some of them. We have friction, we have cohesive behavior, we have material that is elastic, we have material that is plastic, and you have thousands of them. Or in this case, each unit that you see, we have these glues or VHPs that each unit on average has 20 of them, and each has 2 interactions. So adding those numbers, you get a model that it's going to take literally forever to be run with the infrastructure that we had. We could have done this, but if you do it, you're not going to get an answer in a timely manner, meaning it needs months to be run to get an answer. And with the fact, knowing that we have thousands of models or hundreds of models to run, like changing the thickness, running, getting the answer. So this was kind of impossible to do. So the second model that we were thinking was the macro model, meaning we simplified things, and some say it's oversimplifying, that we have just a glass shell as a continuum and the side plates as another continuum thing. Everything is connected. There is no signs of interlocking bar. We consider those parameters within the model somehow. So this model was very simplified, but in some cases we might lose accuracy. So these are basically, we have done this through it was a process through the project, and we realized we need a middle ground. So we came up with something that we call simplified detailed model, something that could predict the behavior of the bridge and be accurate, but at the same time, in a timely manner, it's not going to be expensive in terms of running. By using engineering terms instead of some of those very, very technical forms, by simplifying it, that could predict the behavior of the glass. So this is our simplified model that shows we could reduce a number of interaction, number of material, and have the answer. But the question was, how do we know this simplified model or this detailed model is going to work? Thankfully, we had the test from Joseph. So we had all these information that has been done, and we had the model actually before doing the test. So we had some prediction that how the test is going to behave. And the simplified micro model or detailed model that we had, it was a good match. So the experimental and numerical results, they were in agreement. So we said, oh, good. Our model is predicting such a complex, and this is one of the most complicated problems that I have ever had. And believe me, I've been dealing with a lot of complicated problems. So there is interaction, material, a lot of things going on. So this is what we got, like experimental, numerical. It was a good agreement, like considering all the complexity, getting something that is within 5–10% of error, that was an achievement. And also the deformation, we could measure and compare it with experimental data. So we had faith in this model. Now we know the 10-meter bridge, we are not going to test it, but we have a working model. So we could extend what we have to different model. If we want to change the geometry, we wanted to. Now we have some sort of faith in the model before even getting the green light to go ahead and build it, because we need numbers. We use this very same model to build the 10-meter with all the details that we had. And this is just showing how the connection, how the supports and loading is happening under its own sulfate, and also under a critical loading condition, that if we push this bridge at what load is going to finally break, right? This is a video of our model. So if you wonder how this 10-meter bridge is going to behave, this is how it's going to behave. And this is the worst case scenario, meaning right in the middle of the bridge, if we push it down, just like what Joseph did at Villanova University, that's the worst types of loading. You have a concentrator loop pushing it down. Of course, it's just gonna bend and it's gonna collapse. But we did that, and we look at the numbers, and we realize there are numbers from code that, okay, how much load we should apply. There is a single digit number, 4 kilonewton per square meter. If you apply that and the structure is within the boundary condition of what you are defining as a safety limit, then you're good to go. You could build that. So for instance, the maximum deformation that code allows for such a bridge is like 5 millimeter or 6 millimeter. And if you are less than that, you will be fine. So eventually, and I'm summarizing everything in one slide here, looking at that stresses, we realize the glass is not going to be exploded because the stresses are always less than the strengths of glass. So that's a safety which we here, which sees that's 44 megapascal, and glass is going to carry more than that. And also in terms of this chart, we know that the bridge under its own weight and load, it's going to deflect around 2 millimeter, which is within the allowable condition. So we know if you build this bridge with all the details that we have, the bridge is going to withstand not only its own suffer, even if you apply the load, it's going to be okay. And that's the moment that we were happy and said, okay, let's go and build this thing. Again, we did a lot of experimentation. Every single experiment that we have done, we did the model, and we make sure that the model is actually it's working. With that, I will introduce Professor Jens Schneider, who is not here, but I'm assuming he will be joining through Zoom. Yeah, Professor Schneider is going to talk about the impact of this project. Thank you.
Thank you, Damon, and good evening from Vienna in Austria. Thank you for having me this evening. I just want to talk a little bit about our brilliant collaboration between architects and engineers, because I think the impact that we can have from that is already and was already mentioned by Masoud a little bit, but I want to talk a little bit more about it. Masoud, could you have the next slide, please? So if we're talking about glass material, I've been working with glass since I was in school, and already in school time I was working in window replacement. And this material, of course, comes with its transparency at a cost. The cost is the brittleness, and the brittleness means we always have to work across different dimensions and different scales, because I think many of you in the room will know that micro cracks and nano cracks in the end determine the strength of the material, and it is very difficult to exploit its full potential in compression because of these micro cracks, nano cracks that we cannot avoid during production. But I think the idea we had really had an impact, that we, instead of using massive glass, because massive material is a typical application you would expect from a kind of a arched structure like was shown before. for example, like brickwork. But here, the idea was to really use sheet material or plate material, glass material, because the production in a float glass is very efficient and it's using much less material in the end than using a massive. So then this needs to be engineered in a way that we can look at the detail because of the micro cracks and very, very large influence of these cracks always present, but we don't see it with the naked eye. You have to look at the details and very carefully. And to do so, in the end, in this project came at a very interesting structure in this combination of the side plates and the top plates and the connectors that really give the impression of this kind of bone structure. And this, I believe, will have an impact because we cannot go on like construction we did in the last 50 to 100 years using so much material. And we have to be much more efficient and just reduce the material and don't use material where we don't need it. And this also is a better solution for the glass because you all know that the thermal conductivity of the glass is such that a massive construction will most likely have very large limitations because thermal differences between top and bottom in a massive construction would be very difficult to handle. And because of the sheet materials, it's much more easier. Of course, for safety reasons also here, and in the top plates, we use laminated glass because laminated glass is safe even in case of fracture. And I think the last aspect I just want to talk about is the assembly-disassembly. I think in the future, more and more the engineers will have to deal with the fact that we need a real circular economy. Circular economy means that we want to reuse as much as possible, but this means that already during the planning and the design of the construction, we have to think how to disassemble also in case of reuse later. And of course, this project, like hand manufactured now here, shows a large potential also for future improvement, for example, with robots helping the humans putting the places together and making it even more efficient. But I think the principal idea of assembly and disassembly is very well kept in the idea that these hollow glass units can be manufactured one by one and then later put together like in a big puzzle or brickwork. So I think in total, this impact of the project will be a different mindset, I hope, because I think human imagination is unlimited and human imagination is really needed with the pressing challenges we have in our environment. And we have to keep on working on using our imagination in a way that we can also motivate other people to follow these types of very efficient, material efficient, in the end, energy efficient and CO2 efficient types of structures that help the building sector to reduce its impact on the planet. And this is why I'm really proud to be a part of this project. Thank you.
Thank you very much, Jens. I just wanted to say a few words about also the artwork that has been designed underneath the bridge. So the artwork is a design collaboration with a Swiss-French artist, Romain Grelier, who we had an honor to have him today here. And we had a really good collaboration with Romain because he has extensive experience in creating reflective surfaces. And I reached out to Romain because at the time I was actually looking for an element, a design element within the exhibition space that could emphasize the role of bridge. Obviously, there was no river or chasm that we were bridging over, but and we wanted to really emphasize the fact that this project is bridging over something. just to reflect the beauty of the bridge, the underneath geometry of the bridge. So we had a conversation with Roman, and Roman actually executed really interesting pieces, if you look at his portfolio, made out of recycled oil and as a reflective surface. And that was an excellent choice for us, because we were actually an advocate for a bridge to future. We were promoting the advanced technology, reduction of carbon footprint. So it was the best, I would say, segue to have a fossil fuel underneath that, so that to say that, look, you're bridging over the fossil fuel to reduce carbon footprint. Unfortunately, the regulations of Corning did not allow us to use any kind of liquid in the exhibition space. So that led us to work with reflective surface. And with the guidance of Roman, we were able to execute this beautiful piece underneath. Fast forward to the team who were involved in the construction, many of whom were not able to be here. I thank them all, my team members, and also my former PhD students, Yao Liu and Joseph. We had a privilege working with him today at the time of installation. And people who traveled from Germany, Amir, to be here, Jens, students. So we had a really nice time, and thank you, Corning team and Kate, for really hosting us and letting us work on this project. So as Joseph said, we had an extensive publications on this work. You can find these publications on the Polyhedral Structures Lab website. It's available for you to download. And if you're interested in the methodology that I introduced in the beginning, everything has been collected in a book that I'm publishing simultaneous to this exhibition by Cambridge University Press, and it's going to be, and it was supported by National Science Foundation. In fact, that was one of the reasons that we reached out to Corning to basically showcase and make this science and engineering work accessible to public and communicate with public. Again, another thanks to all the parties and companies involved with the construction. This is one of those moments that you're in the wedding ceremony and you thank everyone, but you forget to thank your mother-in-law, and you sit down. I would say thank you very much to Corning team at the first place. I had a privilege to talk with Susie initially, Susie Silva, when she was here. And she was very much interested in the project, and then the project carried over to Catherine, and then Catherine to Kate. But we had a really good support from Corning that made it possible for us to be here to talking about this project. Thank you.
All right, thank you so much. So I'll invite all 4 of our speakers, well, 3 of our speakers in person and Jens online, as well as we're fortunate to have Roman here to come up to the panel, and Moritz from Glasbau Pritz. So if everyone will please come up for our Q&A session, so we can see your lovely faces. Yeah, so thanks for really shedding a lot of amazing light onto the complexity of that process that we had to kind of bring that glass bridge to light. So we're ready for some questions from the audience. I'll ask if you're on, for those of you online, feel free to put your questions in the chat. We've got somebody monitoring that, and then we have microphone runners, so we ask that if you have your hand up and you have a question, wait for the microphone so those online can hear you. So yeah, let's start with Richard.
A great presentation, thank you so much. A number of speakers, starting with yourself, Masoud, you had spoken about the brittleness of glass as a material to work with. And in tensile application, that is obviously the case, but your bridge is, the principle is compression. And my limited understanding is that the compressive strength of glass is actually much stronger than materials like concrete. So I thought the bridge was an illustration of the incredible strength of this material using its capacity there. Did that factor into your thinking?
Absolutely. I think at the end, that was the entire intention. Thanks for bringing that up. I mentioned brittleness, but as you mentioned, brittleness in tension or torsion out of plane bending, for instance, that's really key. But what we showed here in this structure is that because of the actual geometry, we channeled the forces or controlled the forces to go through the glass always such that we can take advantage of the compressive behavior of the glass. So the thickness of the glass, if I forgot to mention, is only 16 millimeter. So 2 layers of 7 millimeter glass sandwiched with the PVB or the substance in between. That gives us only 16 millimeter thickness plate. So the entire force that we designed for, which is 400 or 800 pounds per square meter load and the self-weight, goes through that cross section, which is very, very small, right? And again, one of the design techniques that we had that allowed that to just we were able to redistribute the force in 2 layers so we can increase the effective depth as it happens in natural structures. But to give you, to again, restate what you said, the entire process was to really take advantage of the compressive strength of glass through the geometry of the structure.
Interesting question. Just for you to know, if you apply masonry in general, and in this case glass, as you said, it's very strong compression. And if you apply, as long as you are in a symmetric loading scenario, if you apply a symmetric loading on this bridge, up to 4 ton, it's a huge number, 4 ton, and still the deflection is very small. The problem is when you go asymmetric. So asymmetric, then it will create tension, and that's why you need a very strong connection. Here, we don't have that. You see those butterfly connection are just plexiglasses, so they are not as strong, and that might cause an issue. But in terms of the form and being in compression, it is extremely strong. So no doubt about that.
Over here. So, okay. What material did you use to assemble the blocks? Like what adhesive, and did you experiment with different types of adhesives?
I think
Yeah, that's a great question. I showed in one of my slides in the beginning, we showed the different components of the hollow glass unit, and there was a roll of red tape in the bottom right-hand corner. I'm sure you don't remember it, but nonetheless, it answers exactly the question you're asking, and that was a double-sided structural tape called VHB tape, and it's manufactured specifically for joining glass. We did not use any different materials, unlike the interface material where we experimented with several different types of transparent materials to find the one that had the properties we needed. We were told by an architect, it was actually at a conference at Jefferson University in 2019, about VHB tape and how he used it all the time in his work, and it is a really, really reliable material for joining glass. So that's what we used, and it functioned beautifully based on the experimental results that we have. Did you want to add anything?
Could you tell us what VHB stands for?
Very high bond. That was a great question too, by the way.
In the diagram, the VHB didn't go to the corners, and I'm wondering, was that?
Excellent observation. Excellent observation. No, the corners were rounded with 5 millimeter radius because you have to avoid very, very sharp edges with the glass because that's going to be a location of stress concentration and cracking. So during the fabrication of the deck plates and the side plates, which were glass in the experimental work, we had those rounded corners. And because we had the rounded corner, we had to terminate the VHB tape before it got to the curvature of the rounded corner and actually back it off a little bit. So you are 100% correct, and there is a void space at the intersection of the side plates and the deck plates.
Carol?
I have a question about art. So, Monsieur Crédit and Masoud. So
First of all, thank you for not pouring used oil on the gallery floor. We appreciate that. But when you realized that couldn't be the artistic material that you were going to use, I'm delighted with this collaboration between this very elegant structure of the bridge and then this beautiful pool underneath it. How much dialogue did you have about what this would look like, what material you would use? I'm very interested to know how that collaboration took place.
Mm-hmm.
I speak in. Ok. C'est des formes que j'ai travaillé, utilisées et dessinées depuis très longtemps. Et puis pour le pont, cette forme qui donne une idée un petit peu de quelque chose de liquide qui pourrait passer sous le pont, nous a semblé avec... enfin, quand j'ai proposé ça à Masoud, je crois que... Je trouve que ça fonctionnait plutôt très bien. Et puis après, c'était, il fallait trouver une taille qui fonctionne et qui soit en fait en équilibre avec la grandeur du pont, enfin avec la taille du pont. Excusez-moi, ouais.
So I'll try my best. The idea was to use, he worked a lot with those forms in his works, and with Masoud, they called and he proposed this shape, not immediately, but in the end, that is the shape they choose, and they were happy with the balance, and they needed to work also with the shape of the room to adapt also with the size of the bridge, and there is something to do with also like it's like a river, like the round shape, and to I don't know, does that? But Masoud, maybe you can say something.
It was a very interesting dialogue because, first of all, I don't speak French, so we had to go through multiple rounds of translation, thanks to Puzzle. I think initially, so there are a couple of intentions that I think we were lucky that we were on the same page, so we didn't have that much fight. So first of all, we were looking for something that could reflect the bridge. We were looking for an object that does not compete with the bridge itself, but in the meantime adds to the quality of the bridge, and it has its own inherent qualities. So the shape of the object was really important because it could be any shape. It's a droplet, right? So it could be just a symmetric circle. It could have multiple. Again, I'm talking very qualitatively, but I think one thing that was really important for Roman and I was that the placement on object and the rotational symmetry or the actual axis of the placement. Because if you look at the bridge actually has a rotational symmetry. You can cut the bridge in half, and you can rotate the part and put it in the other side, and that would give you the complete bridge. There was a reason for that design because we wanted the simplicity, and for construction reason, we wanted to actually minimize the effort. The same thing happened to the art piece, but it was symmetrical, but the placement was asymmetric. And we had also multiple constraints from the site, because the first thing that Roman asked me when he was basically given that task to design was that, okay, you need to give me the geometry of the room. If I don't know the geometry of the room, I wouldn't be able to design that. And then with the particular geometry of the room in mind, we designed it such that we could maximize the effect of reflection. And there's another thing that you don't see And by the way, we didn't want to cover the entire underneath the bridge because we wanted to be very well controlled. Then what you don't see is that underneath that piece, the metal parts are connected with tension tie. So there is a little detail that allows us to control the distance between the supports of the bridge. And that had to be controlled both during the assembly and construction, right? And after that. So that piece very well covers those areas. So we made sure that although we cannot cover the entire tension ties, but at least those connections needs to be covered.
Yeah, it's a little bit of trivia that I like to tell people about the bridge is that it was actually custom designed to fit in that gallery. I think the initial model, they had it a little bit larger. And when we told them the dimensions of that space up there in the Contemporary Art and Design wing, they had to just shrink it just a little bit.
Yeah,
So
just a little. One more point I remember that we had a discussion with Roman, and I think that adds a lot. And that was about the patterning, because we had these limitations of the pieces would be manufactured in China and transferred here. So there's a limitation in the size of the panels that you can build and send and ship without being destroyed. Warren would actually look at me and probably he would laugh because we had some drama around it. But the point was, okay, you can panelize this entire shape into many different ways. So I told Roman that, Roman, I'm sorry, how do you like this to be patterned? Right? You remember that discussion, Basil? Because we can pattern it for you however you like. You know, we can go really crazy, we can go curve patterns, etc., etc. He said that it has to be straight. Just very straight, sharp cuts. Rectangular patterns within a circular form of the pond. So, okay, wait a second, we could have done this many differently. Why do you want? And do you want to ask this question from Roman so he can answer that?
Différentes coupes à l'intérieur de la forme, tu voulais faire de manière différente, tu as choisi de les faire de manière droite. C'est une bonne question. Good question. Ouais. Parce que bah, c'était difficile de revenir avec déjà l'extérieur qui est rond, revenir avec des formes plus circulaires. Il y a la structure du pont qui est quand même qui est très belle et tout, mais qui a une structure qui est quand même déjà au niveau visuel qui est très présente comme ça. Et puis je dois dire que l'histoire, l'idée d'avoir des lignes qui soient par rapport au pont, la direction du pont, hein, enfin, c'est quelque chose de très précis. Moi, je devais aussi avoir quelque chose de très précis qui puisse, comment je veux dire, qui puisse se poser dans l'espace d'une manière à ne pas me faire manger par la structure du pont. Voilà. So there is two things. The first thing is he would not interfere with the geometry of the bridge because it's a really special form, and the other thing was to give a direction to the art form. And as you said, the bridge has a direction, and the idea was to give another direction to the art form, and not to compete, but to work together. So it was.
Thank you. We have time for maybe one more question from the audience. Yes, thank you.
Hi. This is also related to, you're talking about symmetry and asymmetry. I noticed in one of the photographs, the shape of the butterfly connector peg seemed asymmetrical. It may have just been the photograph, but I'm wondering about the shape of that butterfly peg there.
I don't want to be the only one who's answering these questions, but No, the shape is completely symmetrical for constructability reasons, but because of the shape of the bridge, which is not symmetrical because it's an arch, when you cut it in an angle, it might seem that it's asymmetrical, but they're all symmetrical in profile. So one of the ways that we had to make it economical was to create a die or a die cast, because we talked to a manufacturer who can extrude these profiles for us, because that was the most economical way to produce. So all the profile shapes had to be the same shape. So everything that you see is just the same dimensions, but the way that we are cutting the end and the start, because the units are basically coming in different angles, that would make them look like that they're asymmetric, but they're all symmetric.
All right, I'm going to sneak in one more online question.
Hi, everyone. This is from Judith. What applications can you imagine this work can replace, and/or what have you realized about its potential now that you have proved this object can exist? Great question.
Yeah, thank you.
I'll briefly answer and let the rest of the collaborators talk about. So I think the immediate application is that if it works with glass, as I explained, it works very well with other sheet-based material. This is a sandwich layer lightweight structure. You can apply that to any other sheet-based construction material. That is great. The other immediate outcome of this installation, in fact, is that we realize that the system is just really robust, that it can be used for shells that could cover common spaces with maximum transparency. So it doesn't have to be a bridge. It can be a dome for common areas.
Yeah, I would agree with that, Masoud. I think the function of the system as being compression dominant, and also the fabrication of modular technology, just lends itself into large open spaces where you desire a transparent material. So I would cite examples as facades or roofs for stadiums, train stadiums, airports, things of that nature. But any place really where you don't want the limit of a material like steel or concrete that doesn't allow the penetration of light. So it's the transparent quality and the use of the material in the system that really opens itself to a number of different applications in large open space where transparency is desired.
Since 1820, with the benchmark of flat iron building, meaning the introduction of cast iron, changed everything. If you look at the history of architecture, that's a benchmark. Before that, we used to use compression-only structures. You see all these beautiful walls, and arches that were everywhere. But introduction of cast iron, steel, it changed the philosophy of design from compression to bending. And this might be difficult to understand, but bending is just wasting of material. What we're doing here, what this concept of the bridge is going to introduce is that sometimes going back is not that bad. We just need to revive the ideas of sustainable design by using less material, relieving a little bit of pressure from our natural resources. Numbers are not looking good, the way that we are consuming of our mountains to turn into concrete, because we are just wasting tons of concrete to construct a beam, a structure. We could, I'm not saying we're not going to use it, but let's use it efficiently. Just in a simple research that I've done, we could reduce 500,000 pounds of concrete in one single construction without affecting its structural performance. And going back to compression-only structures or using tension compression could significantly help our environment and negative impact that we have on nature. So the glass bridge, you might think, yeah, this is impractical glass. That car is gonna pass it. Is this a footbridge? What it is? It's beyond, the idea is beyond this. This is just a concept to show that we are able to do that, right? So in terms of materiality, as Masoud said, sheet structures could be replaced, like we could use other sheet, even wood, and to produce these very, very strong structures with much less material. And that's how the future of architecture is going to be, and how I personally teach my students that think twice. We don't have all the material. We need to think about the future generation. And this is just one way of optimization of what we are using, which wasn't the case 50 years ago. We thought we have everything, but now we see the negative impact, and we have to go back and revitalize some of those good ideas, bring them back.
I think that's a really great note to end on. Unless Jens, did you want to add anything to that?
Maybe just only one thing. I think what is really interesting is that this type of material, this float glass, was relatively cheap. Why? Because it's not bent. It's flat. But if you see the result, because of its additive type of hollow glass units that we put together, it looks a 3D object. So I think this also adds to the idea where we could use it, everywhere where you want to have compression dominant structures and want to use only 2D flat material as sheet material. You can use it by the method that Masoud developed, and then end up with a very elegant 3D structure. So that's the only thing I would add to that. Thank you.
Thank you. So let's continue this conversation up in the presence of the bridge. So I'd just like to thank again all our presenters, to Jens especially for staying up until 1 o'clock in the morning, 2 o'clock in the morning now, to everyone who came from distant places, to our amazing Corning events and AV team for pulling off such a great event. Again, to the Corning team who was involved in the exhibition, the publication, and everything else that kind of on our side that helped this come to fruition. So those in Corning will take the escalators or the elevators upstairs to the Special Projects Gallery of Contemporary Art and Design. There will be folks along the way to guide you. And this is a special opportunity to see the bridge at night, and it's spectacular. So even if you've seen it or you think like, oh, I'll come back and see it another time, like, go see it at night. This is your chance. It's gorgeous. It just takes on a totally different life. And yeah, those online, I hope you visit soon. The bridge will be up through Labor Day weekend, September 1st, 2025. So we hope you'll be able to join us. So yes, thanks again for joining us this evening. Thank you.